All right, we're going to be talking about radioactive decay today. So radioactive decay basically just means that certain things decay over time. So radioactive decay means that certain things decay over time. Means to decay over time. So the certain elements that do this are going to be listed on the front of our reference tables. So this chart on the front of our reference tables is going to help us a lot. So certain elements decay over time. The elements that do this are on the front right here. So carbon 14 is one of them. The second one is potassium. Third one is uranium. And the last one on this list is rubidium-87. So it actually is important, those numbers at the end there. I forgot one of them as I was doing this. But you do want to make sure that you are writing them because it's what it is the number of things that are in the nucleus of the atom. So maybe you've talked about before in an atom, there's a nucleus. So carbon describes what kind of element it is, but not all carbon is radioactive. Only the carbon 14 is actually going to be radioactive. So if you're asked to describe something that's radioactive or decaying to something else, you're going to want to write carbon 14 or potassium 40 or uranium 238, not just the name of the elements. So the reason we like to use half-lives is because it can tell us how old something is. So it can tell us how old something is. The way it can do this is if we look at this table on the front of our reference tables, we see that carbon 14 is listed with an arrow to nitrogen 14. So that means that carbon 14 is going to decay into nitrogen 14. And the way this works, the reason it's radioactive is it happens on these half-lives. So carbon 14 is going to decay into nitrogen 14 using this 5.7 times 30 years. I'm going to frequently write that as 5,700 years. It's the same thing, just not in scientific notation. All right, so let's go back down to this area. The way this helps us is basically what's going to happen is we're going to start off with 100% of our carbon 14. So we have 100% of our carbon 14. And this is after 0 half-lives. And then we're going to move on, and after 1 half-life, well, this is going to be broken up into 50% carbon 14 and 50% nitrogen 14 now. So it's called a half-life because after 1 half-life, half of it has decayed. Now, the nitrogen 14 isn't radioactive. So all of this nitrogen 14 that we have, we're still going to have all of that nitrogen 14 left. But of this carbon 14, we can do arrows here, of this carbon 14, half of that carbon 14 is going to decay into nitrogen 14. So instead of having 50% of where we started off, we're only going to be left with 25% of our carbon 14. So now this arm right here, this represents 25%, because it's also 25%. And this was 50. So how much nitrogen do we have left? Well, we have 25% from up here, 25% nitrogen from here, nitrogen 14. But here we have 50% nitrogen 14. So overall, we have a total of 75%. And this is all after. All right, so we're going to fill in some more information. So half-life, again, is how long it takes for half of the parent to decay. And it depends on what kind of element is being decayed, but for a specific kind of element, it's always going to be constant, right? So carbon-14 is going to decay at a different rate than potassium-40, but all the carbon-14 ever in the world is going to decay at the same rate, and all the potassium-40 in the world is going to decay at the same rate. Potassium-40 is not the same as carbon-14, but all potassium-40 is the same, all carbon-14 is the same, all uranium-238 is the same, and all rubidium-87 is the same. So one thing you'll notice when you look at the cover of your ESRT, and you look at those different half-lives, so again, that's this guy, we'll see that carbon-14's half-life is 5.7 times 10 to the third, whereas all of the others are times 10 to the 9 or times 10 to the 10. So what does that tell us? So that's going to tell us that if we want to find something, if we want to find out how old something is, and we suspect that it's on the order of 5.7 times 10 to the third years, right? It's close to 10 to the third years, then we're going to want to use carbon. If we think it's much, much, much older than that, we might want to use potassium or uranium. And if it's even older than that, we may be wanting to use rubidium-87, right? So how old we suspect something is going to affect what type of element we're looking at to determine its age. So again, carbon-14 is good for short periods of time. Potassium-40 is going to be good for really long periods of time. And uranium is going to be good for long-term millions of years, the oldest rocks on Earth. So that's the rough idea of how different elements are going to affect how old the rock that we want to look at. We're just going to look at again how this half-life of carbon-14 works a little bit more specifically. So again, carbon-14 has a half-life of 5,700 years. So that means that half of it, or 50%, is left after 5,700 years. And after 2 half-lives, we're going to be left with 50% of that left as carbon. And half of a half is a quarter. So we have a quarter, or 25%, left after 114,000 years, or 5,700 years times 2. Had an extra 0 there for a second. That is 11,400 years. And this pattern is just going to keep on happening as long as this carbon-14 can go on. So let's try it. If I start with 100 grams of sugar, and I know that sugar's half-life is 2 years, so in 2 years I will have 50 grams left. In 4 years, that's another half-life. So in 4 years, I will have 25 grams left. And in 6 years, now this is another half-life. My time hasn't doubled, but another half-life has gone by. I've gone from 4 years to 6 years. So that's, if a half-life is 2 years, that's another half-life. So my 25 grams of sugar is going to be cut in half. So instead of having 25 grams left, I will have 12.5 grams left. So every 2 years is one half-life. So over the course of this decay, I have had 3 half-lives pass. I hope you enjoyed this video on radioactive decay. I'll be more than happy to help you as you work on some of the stuff related to this topic.